Hi, I'm Rob Hillis, Chair of the Friends of the Institute, and it's my pleasure to welcome you to our first Friends Evening Talk of the spring term. I am delighted to introduce today's speaker, Sukanya Chakrabarti, a professor of physics and astronomy at the Rochester Institute of Technology, and a 2020-21 member and IBM Einstein Fellow in the School of Natural Sciences. Dr. Chakrabarti earned her undergraduate degree from North Carolina State University and went on to University of California, Berkeley for a PhD in physics. She was an NSF Fellow at Harvard from 2005 to 2008, and then returned to Berkeley for 2 years as a UC Presidential Postdoctoral Fellow. She's been a member of the faculty at RIT since 2013. Much of Dr. Chakrabarti's work is focused on trying to understand the nature of dark matter, and more recently, time domain astronomy. Her theoretical research centers around the formation and evolution of galaxies, with the goal of developing astrophysical probes of fundamental physics. In addition, she actively uses observing facilities, including the National Radio Astronomy Observatory and Las Cumbres Observatory. She has published numerous papers, both on her own and in collaboration with others, and she has served over 1,000 hours as principal investigator or co-investigator for many proposals. Sukanya has also authored a great number of articles appearing in Science News, Scientific American, Astronomy Magazine, National Geographic, Sky and Telescope, Earth Sky, and Vice, to name a few. And she appears often as a speaker in both academic settings and for a general audience. She enjoys teaching physics and astronomy at the undergraduate and graduate levels and communicating science to the public. With a strong commitment to enhancing diversity in academia, she is a member of the Committee on the Status of Women in Astronomy, the Women in Science Executive Committee, and the Council for Representation and Engagement for Women. We greatly appreciate Sukanya's taking the time this evening to discuss using galactic clocks to map dark matter. Please join me in welcoming Sukanya Chakrabarti. And just a quick note, you'll notice you're getting a transcript down below if you can turn on subtitles if you are not seeing it.
Thank you. Thank you so much for that wonderful introduction. Before I get started, I just want to say it's been really a privilege for me to be here at IAS during my sabbatical and to have the opportunity to do the work that I'll talk with you about today. And I wish I were talking with you in person, but under the circumstances, I'm happy to at least have the opportunity to talk with you remotely. So I'm going to talk today about techniques that we've developed over the past year to directly measure the very small accelerations of stars that sit within the gravitational potential of the Milky Way. So when I talk about this, I like to refer these very small accelerations that we're measuring, that we now can measure due to advances in technology, are a few centimeter per second over decade baseline. So this is about the speed of a crawling baby and not a very fast baby at that. These measurements of pulsar accelerations, these fantastic galactic clocks called pulsars, have allowed us to directly measure fundamental galactic parameters and learn important new insights on, in particular, on the distribution of dark matter in our galaxy. But before I talk about that, let me briefly review some of our understanding of the universe as we understand it currently. So this is a computer simulation of growth of structure in the universe, starting from initial conditions prescribed by observations of the cosmic microwave background, where very small fluctuations are amplified by gravity to produce the galaxies and galaxy clusters in the universe today. And if you take a slice through such a virtual universe, that's what's shown here in the red, and the real universe is shown in the blue. And you see that there's a very good degree of statistical correspondence. Now, more recent simulations that have been done by the astronomy community have included additional physical effects, such as the effect of supernovae going off and polluting the surrounding interstellar medium with heavy elements that are necessary for the process of for life on Earth. But the fundamentals are still very much the same. One of the key components of this paradigm, the cold dark matter paradigm, that has been very successful at describing the growth of structure in the universe and a variety of observations, is this mysterious dark matter. It is very fundamental to explaining a wide range of observations, but we still don't really understand what it is. And that is one of the reasons why we embarked on this study. So the traditional methods in astronomy that we've used now for more than a century is to estimate accelerations using observations of the positions and speeds of stars. However, this method assumes that the galaxy is in equilibrium. And now there are many indications that the Milky Way has been perturbed by dwarf galaxies. There are many manifestations of non-equilibrium phenomena. And here's one example. What's shown here are the vertical velocities of stars as a function of vertical height. This is from the Gaia satellite mission. And you see a spiral structure in this domain, which you wouldn't expect if the galaxy was purely in equilibrium. And this has been interpreted as having arisen due to an interaction with a dwarf galaxy. An earlier work from an analysis of ground-based data showed that there is a north-south asymmetry in the star counts, such that it looks like the galactic disk is wobbling. So there are many indications now, there are many different lines of evidence that our galaxy has a time-dependent potential, that it has had a highly dynamic history. And people have also shown that the true acceleration in an interacting galaxy is in fact different from what are called these kinematic estimates, where you use positions and speeds to estimate accelerations. So these are some of the motivations behind why we wanted to try and make direct measurements of the galactic acceleration. And it's the accelerations really that give us a direct window into the masses and the forces. And the masses here include, of course, the masses of the stars and this invisible mysterious dark matter. So here's a computer simulation that I've done of the Milky Way interacting with the Antlia 2 dwarf galaxy. And you see that Antlia 2 perturbs the disk of the Milky Way. This shows the stellar response. And here you see the gaseous responses. The Milky Way interacts with this dwarf galaxy. So the two techniques that I'll talk about today are measuring the acceleration by using very high precision measurements of the change in the velocity over decade baselines. And the second method that I'll talk about is work that I've done here using these fantastic galactic clocks called pulsars. These are rapidly spinning compact stars that have a temporal stability that exceeds that of atomic clocks even. And by using these, we can basically, we have essentially galactic accelerometers that we can use to measure these very small accelerations of stars within the galaxy. So let me start with the first method, that is measuring accelerations by measuring the change in the velocity, measuring very small shifts in spectral lines with very high resolution spectrographs. This technique and other techniques have been used by the exoplanet community. The work that they're doing to hunt for planets around other stars. This is an example here. Particularly the discovery of the low mass planets. This particular planet system has a couple of Earth mass. Requires very high precision measurements. So as the planet goes the star, the planet also tugs on the star. Okay? And as the planet tugs on the star, you see these very small shifts in the spectral lines that can be used to characterize the planets. So this is the first technique that I'll talk about. And advances in the precision of these kind of instruments, of these spectrographs, have improved dramatically in the last few decades. So you see here the radial velocity precision as a function of the commissioning year of the instrument. And we're in the 2020s, and we have access to, see if I can use my laser pointer. So we have access to instruments like Espresso, and in the future, we'll have access to instruments like Codex. So Espresso on the Very Large Telescope in Chile has demonstrared a precision of about 30 centimeter per second on quiet stars. And so it now gives us the opportunity to begin to make these kind of real-time measurements that I think will really ultimately form the backbone of what I like to call real-time galactic dynamics. So this, as I was saying, I like to compare the galactic signal to trying to measure the speed of a crawling baby. So here's a crawling baby. But when you're looking at the galaxy and trying to measure the changes in speeds of things, you're not just looking at stars. You also have planets going around their stars, and as you saw, some of them can produce a signal that's comparable to the kind of signal that we're going after. And you also have binary stars. They're stars that are going around each other. Okay, so these are the bunnies, and you can see the bunnies are going faster. They're outpacing the babies. So you really have to think about a population of single stars that faithfully trace the galactic signal. That's shown here. This is a histogram that shows the effects of the full population. The stars are shown in the blue. The stellar binaries, stars going around each other, are shown in the green. And the planets, the snails, are shown in the red. And so you see that the binaries do have a large change in the velocity, so it'll be easy to call them from our sample. There are some planets, the inset shows a zoom in close to the galactic signal, and you see that there are some planets that do overlap in the regime where we're trying to make the measurement. But in typical realizations, it's really a very small fraction, a few percent. So we can expect that with a sample of about 60 stars or so, we should be able to recover the signal with these kind of extreme precision radial velocity measurements to very high statistical significance. Okay, so for the rest of my talk, I'm going to talk about the work that I've done since I've been here, using pulsars, which are very compact, very rapidly spinning stars that have extreme temporal stability. Okay, so here is an example of that. This is actually a slow pulsar. And you see, you can hear as well, sort of this lighthouse effect. And you see the pulse profile at the bottom. The best clocks that we have actually are these millisecond pulsars that spin hundreds of times a second. And here's an example of that. And this is in the radio. So this is actually what it would sound like if you heard it. So in particular, what we look at is the change in the orbital period of pairs of pulsars, or the change in the orbital period of binary millisecond pulsars. And by monitoring this change, we can essentially use them as galactic accelerometers, very much in the same way as the accelerometers that you have on your iPhone, which is how your iPhone knows which way is up or down. So we've got these fantastic galactic accelerometers distributed throughout our galaxy. And this is an image from the press release that we did earlier this year. So you see these 14 binary millisecond pulsars, and we've had to carefully select the best pulsars for this purpose. The sun is shown here in the yellow. Also shown is the Milky Way, and you see this wobbly disk due to the north-south asymmetries that was discovered in analysis of Sloan ground-based data. And you also see here, let me see if I can use my cursor. Yeah. So you also see the tidal debris of the Sagittarius dwarf galaxy. That's what this plume of stuff is here. And this this occurred as the Sagittarius dwarf got too close to the Milky Way, too close on its orbit to the Milky Way, and was cannibalized in the process. So yet another manifestation of non-equilibrium phenomena, interactions that have shaped the dynamical history of our galaxy. So given the accelerations that we have been able to measure directly for the first time, we can derive some fundamental parameters that describe our galaxy. So here are a few of parameters that we've looked at. Firstly, the total mass density, which is known as the Oort limit. And given our measurement of the total mass density, we can subtract out the mass density of visible stars, which leaves us with the measurement of the local dark matter density from these direct acceleration measurements. This is a cartoon schematic of the structure of our galaxy, which is, you see that you expect, our expectation is that the dark matter is distributed in a spherical manner, and the visible stars are distributed in a disk. So we also were able to get constraints on the shape of the galactic potential. That is, how is the material that's traced by the pulsars, how is that distributed? Is it like a disk, or is it more similar to a spherical halo? And finally, one of the early indications that of dark matter in galaxies were observations of these rotation curves, that is, the circular speed of stuff in galaxies. And based on the visible matter alone, when astronomers measured these so-called rotation curves, what they had expected based on the visible matter was that it would fall off in this way, as shown in the red. But what they saw, in fact, and this is because, you know, the density of stars is falling as you go to large distances from the center of the galaxy. But what they saw, in fact, was that the speeds of stuff going around the galaxy was, in fact, fairly constant, even as you move to large distances, where the stellar density is very, very low. So what supports these flat rotation curves? What causes these flat rotation curves? So astronomers had to invoke this invisible dark matter to explain these flat rotation curves. So we wanted to see if we could also derive the slope of this rotation curve, that is to see, is it flat or is it not flat, from these direct acceleration measurements. So this is, these are our results now. This is our value for the Oort limit, which is the total midplane density, total galactic midplane density. This is shown here in units of solar masses per parsec cube, but I'll give it to you in just a minute in more commonly used units. And we can subtract off the density of visible matter, the density of stars and gas, and this gives us the local dark matter density. So I've shown here our value of the local dark matter density overplotted with earlier values. So what's shown is the local dark matter density that, as in published papers, going back about a century. Okay, so you can see that, you know, there has been a lot of work done in this area. And the INSAT shows more modern estimates, and we are, this is our work here, we are somewhat below the typical value, but the error bars in this first direct acceleration measurement are still pretty large. So it's probably too early to say that there are discrepancies. So the stakes for these kind of measurements are pretty high, because all of these parameters affect direct detection experiments for dark matter that are conducted around the world. So we were also able to get constraints on the shape of the potential. And what we find is that the oblateness the oblateness traced by the pulsars is more similar to that of a disk rather than a spherical halo. Okay, so our pulsars cover a region of about a kiloparsec in a radial distance and vertical height that's several thousand light years in radial distance and vertical height. And so it's not a huge distance, but nevertheless, what it allows us to do is get significant constraints in the smaller dimension that is in the vertical dimension. So you can see here our Oort limit, for example, is constrained to about 3 sigma. However, our constraints on the slope of the rotation curve, which is given here, we had pretty large error bars on the slope of the rotation curve. So these parameters affect direct detection experiments for dark matter that are conducted across the world. In particular, the recoil rate is directly proportional to the volume density of dark matter, as you might expect. So here's I'll just talk briefly about things that we have started to do. Oh, sorry, I should mention this before I go on. So this is in more commonly used units. This is the average volume mass density of dark matter. Okay, so in grams per centimeter cubed, it's a very, very small number. But you can also think about how much dark matter you would have within the volume of the Earth, and it's less than a kilogram. So you can compare that to how much gold is produced. It's about 1 million kilograms of gold that's produced every year. So pound for pound, dark matter is more valuable than gold. Okay, so just briefly, I'll talk about the work that we're doing now and what we'll be doing in the future. So we've been able to measure a smooth, sort of essentially smooth component of the acceleration directly. But galaxies, as shown here, have a lot of structure. The mass distribution is very, very discrete. Okay, so you can also expect that there might be sort of, because of this discrete mass distribution, both from the stars, and we expect the dark matter to also be in clumps in our popular models, that is dark matter substructure, that there might be, if you have a very densely populated sample, that you might be able to measure sort of jerks in the acceleration. So we're going to try to do this with the high precision radial velocity observations. This is a proposal that we just submitted today, which compares our pulsar sample shown in the blue to the more densely populated sample that we're aiming to get high precision radial velocity observations of. So with this sample, we should be able to not only measure the smooth acceleration, but also the non-smooth acceleration. This is George Costanza trying to navigate New York City traffic. And yeah, not all accelerations are smooth. And we'd like to be able to measure both the smooth and non-smooth accelerations. And of course, in our case, it's not cars, but rather the discrete mass distribution of star matter that we're trying to get a constraint on. Okay. So let me go ahead and summarize with these carefully selected 14 binary millisecond pulsars, these fantastic galactic clocks. We've been able to directly measure the galactic acceleration for the first time, from which we've been able to derive a number of fundamental galactic parameters, which can inform direct detection experiments for dark matter. So our value for the total midplane density, the Oort limit, and local dark matter density are close to, but are lower than modern estimates. And our error bars are still large in this initial study, but we are pursuing larger samples, and higher precision data will also be released in future data releases by these pulsar timing or international collaborations from which we compiled our data. We find that the shape of the galactic potential as traced by the pulsars is more similar to a disk rather than a spherical halo. And there are still, in our determination, there are still large uncertainties in the slope of the rotation curve, but it is consistent with being flat. And now one of the things we're focused on doing is combining these two techniques, combining high precision radial velocity measurements and pulsar timing, which may give us a window into dark matter substructure and also constraints on post-Newtonian parameters that may be important for the pulsar community. So I'll end there, and thank you very much for your attention.
Sukanya, thank you for your very provocative talk. And people can raise their hands and ask questions, but I'm going to steal the first one for myself. Are there any reasons why different galaxies might not have substantially different amounts of dark matter as a potential of their total matter?
Yeah, that's a great question. And in fact, different galaxies we think do have different amounts of dark matter. We find that dwarf galaxies, the smallest galaxies, have more dark matter relative to their visible matter than spiral galaxies, the kind of Milky Way in a spiral galaxy in which we live. At the moment, this particular the two techniques that I talked about today, high precision radial velocity observations and pulsar timing, both of these techniques, we can only use them, within our galaxy, because if we go beyond our galaxy to Andromeda and even more distant galaxies, we're looking at even fainter things, right? And as you saw, at the moment, we're only able to look at about a kiloparsec in radius and vertical height. So we're even limited in this direct acceleration technique to relatively close to the solar neighborhood. And that will change as we have better and better instruments. And ultimately, we may be able to make these direct acceleration measurements in, say, my expectation is about a decade from now in external galaxies.
It's very exciting. Let's see what we've got in the way of questions. Pamela, do you?
Ashutosh has a hand raised.
Hi, Pamela. So hello, Sukanya. Nice presentation. I'm not a physicist or astrophysicist, so I will have two very lay kind of questions. One is, I'm still wondering, has the presence of dark matter and dark energy proved, or these are still hypothetical possibilities?
Yeah, that's a good question. So the cold dark matter paradigm that I talked about has become very popular because it is very successful at explaining a wide range of observations. And we are unable to explain many things without invoking dark matter and dark energy. So, for example, one of the things that is these observations of these flat rotation curves, right? When astronomers made these measurements, circular speeds of stars in the galaxy, they expected the circular speeds to drop off as you're looking at larger and larger distances, because there are very few stars out there. So what is producing those flat rotation curves? So that's why dark matter, that's one reason that dark matter had to be invoked, and there are a number of others. That is to explain observations. Now that's and there are similar reasons for dark energy. But that's different from saying that it's been proved, because we don't yet understand. One of the reasons that both dark matter and dark energy are really such fundamental puzzles for decades now in modern astronomy is that we don't really understand what these things are. That is, we don't know what the dark matter particle is. So that was one of the motivations between us trying to develop these new techniques and try to sort of push the envelope a little bit.
Okay. Thank you. My second question, if I still have the permission to ask, I heard recently that the rate of expansion of the universe is actually accelerating, while this is counterintuitive. We all would have expected to decelerate. The rate of expansion should go down, but it is accelerating. Why is that happening?
Right. So that was seen by observations of supernovae at high redshifts. And these supernovae are dimmer than expected in a case where if there were no acceleration. And so that's where that statement comes from. The models that I showed you include the effect of this cosmic acceleration, this dark energy, and the growth of structure that we see actually when we look at the real universe matches also the predictions models. That's yet another reason. But the most direct evidence comes from looking at these supernovae at high redshifts when the universe was younger, and we see that they're dimmer than we expect. And supernovae are they're basically, they're standard candles. Okay, so you can know how, you can expect very well how bright they should be.
Okay, thank you so much. I have one more question, but I'll stand in the queue because I only took permission for 2. I'll ask one more question later on if I still have time.
Thank you. Other questions? Yes? Gopal? You're muted. You're muted.
Yeah, I'm
There we
just waving hand.
Okay.
Hello, hello, hello.
Hi.
We used to be together at IAS. There was a time in 19, which year you and my daughter were children at that time and studying together. Yeah.
Oh my gosh. My parents were here, my parents were here at IAS.
Yes, at that time.
Many years ago. And yeah, my brother and I, and when I first came here, it feels very familiar to me. I mean, not this background, but I'm sitting in my IAS apartments, and it felt.
Which year was that? I don't remember now.
Gosh, I don't remember exactly, but I think we were. I think I was maybe in middle school. Maybe I'm not entirely.
Yeah, may have been in 87, you think? 87, 88?
It could be, yeah.
Yeah, so my daughter, of course, remembers you very well.
That's wonderful. Where is she based now?
She is at MIT. She does neuroscience, and so she's a professor in neuroscience at MIT.
Oh, wow, that's wonderful.
Very nice to see you after so many years.
It's great to see you. It's great to see you.
That's marvelous.
Yeah.
Okay, Ashutosh, we'll let you ask one more question then.
Okay, sure. So thank you. So my question was, Sukanya, you talked about jerks in the acceleration. Is that somehow related to the gravitational waves, or that is entirely different thing?
Yeah, that's a great question. So, these pulsar timing observations were carried out by these international collaborations like Nanograv in North America and others in Europe and Australia, these pulsar timing arrays. And these are very large collaborations that have been monitoring the emission of pulses from pulsars for decades. And their goal is to try and measure the to measure gravitational waves and the stochastic gravitational wave backgrounds. we use that data. We use data compiled from those observations to make measurements in our fields of galactic dynamics. But the main goal of those collaborations was, in fact, to look at gravitational waves. And it's interesting because the precision that you need to do that is in fact comparable to the precision that we need to make measurements of the direct accelerations, these very small accelerations of stars in the galaxy.
Yeah, and these, sorry.
Peter, did you have a question? I'm sorry. No? Okay.
I do.
Okay.
Sukanya, were you surprised, as I interpreted what you were discussing, the amount of dark matter is very small within the Milky Way galaxy. Was that in any way surprising to you?
Right. Yeah. So, yeah, I'm glad you pointed that out. Yeah. So, previous estimates also do find that the relative density of dark matter close to the galactic midplane is smaller than, by a factor of several, than the density of visible matter that is stars and gas. So that in and of itself was not surprising. As you go to larger galactic heights, so this is the galactic midplane, as you go to larger galactic heights relative to the midplane, the contribution from dark matter does increase. But we were only probing about a kiloparsec, several thousand light years in vertical height. So, in the future, as we're able to probe larger distances, we should see more of a contribution from dark matter. But this particular value, or at least the relative sense of it, with the dark matter density being lower than the density of visible matter, is not surprising, and it is in line with previous measurements. However, as you saw, our value in absolute terms is lower than modern estimates, although the error bars are still large.
So could you have had dark matter just more evenly distributed throughout the whole universe, but less close to the density where you have galaxies, because you've got a lot of space around without anything in it, right?
Yeah, so we're only able to get measurements in our own galaxy.
Understood, yeah.
And so we, given the small sample of pulsars, we can't yet, understand in detail how the dark matter is distributed. So we don't, it's not covering, the pulsars aren't covering a very wide range yet. But as we get more measurements that are more precise, and as we look at pulsars that are further away, I think we'll be able to get a better handle on some of these things.
Thank you.
Okay. Other questions?
Can you ask one more question, Pamela? Ashutosh here.
Okay.
Yeah. So, Sukanya, why the discovery of gravitational waves? I think it was for the first time discovered, I think in 2015, right? So why this was so much important? Some people were saying that that basically that was a very, very big moment for the scientists. So why it was so much critical?
So, I guess there are a few reasons. One is it is a direct confirmation of Einstein's theory in the limit where you're directly probing the merger of black holes in the highly relativistic limit. And in that limit, you can't do the calculations analytically, and you have to do these calculations of the merger of black holes numerically. And those predictions had been made by detailed computer simulations. And what we saw with LIGO, LIGO Virgo, matched very well with those predictions. And in addition, it gave us a new window into the universe. Everything that we had seen previously was through the electromagnetic spectrum. And so it gave us a new window into an understanding into the universe. So it's when we think about gravity, we're mostly thinking about Newtonian dynamics, right? And with these observations that the LIGO-Virgo collaboration did, they're probing gravity at a very, very different scale. That is, very close to the black holes when they're merging, or they're in the process of merging. So that's another reason.
Thank you. Thank you so much.
Thank you. I think those are all of the questions. I'll invite Rob to take us out.
Sukanya, thank you for your talk this evening. It was a great treat for all of us, and makes the friends relationship with the Institute just reinforces how special that is. So we thank you for that. And I'm happy to hear of your extended relationship with the Institute going back to your childhood. That's terrific. So thank you again.